When a product's privacy posture degrades, it often happens quietly, not through a dramatic redesign, but through a small change that seemed harmless at the time. A developer adds a new analytics event and includes a user identifier for convenience. A logging statement accidentally captures a full request body, or an SDK update begins transmitting extra device attributes by default. These shifts are privacy regressions, meaning the system becomes more invasive, less transparent, or less controlled than it was before, even if no one intended to change privacy behavior. Privacy regressions are especially common in fast-moving web and mobile environments because releases are frequent and small changes stack up quickly. That is why privacy work cannot stop at design and policy. It must include the practical discipline of reviewing code for privacy-impacting changes and monitoring runtime behavior for drift after deployment. For beginners, the important idea is that privacy is a property of system behavior, and behavior is shaped by code and by the way code runs in production. The goal in this episode is to learn how to detect and prevent privacy regressions by combining code review habits with runtime monitoring that focuses on what data is actually being collected, stored, and shared. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at CIPT.me in the Bare Metal Study Guide series. A strong foundation is understanding what counts as a privacy regression, because beginners often focus only on major data breaches and miss the slow creep that creates exposure over time. A privacy regression can mean new categories of personal data are collected when they were not collected before, or more precise data is collected than before, such as moving from approximate to precise location. It can mean retention increases, such as logs being kept longer or data being copied into a warehouse without a deletion path. It can mean sharing expands, such as new third-party endpoints receiving identifiers or content data. It can also mean user controls become less effective, such as a setting that used to stop data routing now only hides a feature while data continues to flow. Another regression can occur when a system becomes less predictable, such as collecting data earlier in the flow before the user sees an explanation, which increases surprise. These regressions are not always visible to users, but they change the privacy risk profile and often violate internal commitments. Beginners sometimes assume regression implies malicious intent, but most regressions are accidental, driven by convenience, troubleshooting, or library updates. Recognizing regressions as normal failure modes is what motivates building guardrails rather than relying on personal vigilance alone. Code review is the earliest practical checkpoint for preventing regressions, because it is where changes can be stopped or adjusted before they become live behavior. Privacy-aware code review does not require every reviewer to be a privacy expert, but it does require a shared set of questions that reviewers apply consistently. When code touches data collection, logging, analytics, identifiers, storage, or vendor integrations, reviewers should ask what data is being handled and whether the change expands what the system collects or shares. They should look for new fields being added to event payloads, new logging statements that include user inputs, and new network calls to third-party domains. They should also pay attention to default settings and feature flags, because a feature that is off in the interface can still collect data in the background if the code path runs. Beginners sometimes think code review is about style and correctness, but privacy-aware review treats data handling as a correctness issue because collecting unnecessary personal data is a defect, not a neutral design choice. The most practical reviews focus on what the new code will cause the system to emit, store, or transmit, because that is where regressions are born. When these checks become routine, teams catch problems while changes are still small and cheap to fix. A key element of privacy-aware code review is understanding where personal data can leak unintentionally, especially through logs and error handling. Developers often add logs to debug issues, and those logs can capture identifiers, full URLs, and user-provided content without anyone noticing the privacy impact. Error handlers can capture stack traces and context objects that include sensitive payloads, especially when they serialize entire request objects. Client-side error reporting tools can capture screen states or form fields, which can unintentionally collect sensitive information users typed. Beginners often assume logs are internal and therefore low risk, but internal access can be broad and logs are frequently forwarded to external observability platforms, which increases exposure. Privacy-aware review looks for patterns like printing variables that might contain user content, logging entire objects, or including query parameters in logs. It also looks for changes that increase log verbosity in production or that store logs longer than necessary. The goal is not to eliminate logging, because logging supports reliability and security, but to ensure logging is structured, minimized, and scrubbed of sensitive fields. When logging practices are disciplined in code review, the system becomes less likely to create accidental shadow datasets that are hard to delete later. Another regression hotspot is analytics instrumentation, because analytics systems thrive on detailed event streams, and because adding events is easy. A developer might add an event for button clicks, screen views, or conversion steps, and include user IDs or device identifiers to make analysis easier. They might include product names, search terms, or free text inputs, which can be sensitive depending on context. In-app analytics can also pick up device attributes like installed apps, network details, or location hints, especially when using third-party SDKs with broad default collection. Privacy-aware review asks whether each event is necessary, whether the payload includes only what is needed, and whether identifiers are required or can be replaced with short-lived session tokens. It also asks where the event is sent, whether it is sent to multiple destinations, and whether user settings affect routing. Beginners often think analytics is harmless because it is for measurement, but measurement data becomes profiling data when it is linkable and retained long-term. Review should therefore consider retention and access, not only event creation, because an event that is safe for short-term debugging may be risky if stored for years and shared widely. When analytics instrumentation is governed, teams can still learn from data without turning every interaction into a permanent behavior record. Code review should also pay attention to identity and linkage changes, because small identifier changes can dramatically increase privacy risk. For example, adding a stable device identifier to events can allow cross-session tracking that was not possible before, and linking an anonymous session to a logged-in account can make earlier behavior retroactively personal. Adding cross-device syncing can create linkability between contexts that were previously separate. Beginners often assume identity is just login, but identity and privacy is also about how records are joined in databases and analytics warehouses. Privacy-aware review asks whether new joins are being introduced, whether identifiers are being reused across purposes, and whether the same identifiers are being sent to third parties. It also asks whether the system can function with purpose-scoped identifiers, which reduce the ability to link across contexts. When identity changes are reviewed carefully, you prevent silent expansions of tracking capability that users did not anticipate. This is especially important when code changes introduce new data lakes or warehouses, because centralization makes linking easier and can turn many small datasets into a unified profile. Preventing regressions here is about preserving boundaries, not just protecting secrets. Even the best code review cannot catch everything, because runtime behavior can change through configuration, data content, user behavior patterns, and third-party updates. That is why monitoring runtime is the second half of preventing privacy regressions, and it is the way you verify what the system actually does in production. Runtime monitoring in a privacy context focuses on detecting changes in data flows, not on tracking individual users for curiosity. You want to know whether new events appear, whether event payloads gain new fields, whether sensitive fields appear in logs, and whether new network endpoints receive data. You also want to know whether retention settings drift, whether data volumes spike unexpectedly, and whether user settings are being honored in practice. Beginners sometimes assume monitoring is only for security incidents, but privacy monitoring is about drift detection, catching regressions early before they become systemic. A good mental model is that monitoring watches the system's data exhaust, the signals it produces, because privacy risk often increases when exhaust becomes richer and more linkable. Monitoring creates feedback that complements code review by confirming that intentions match reality. A practical form of runtime privacy monitoring is schema and payload monitoring. which means watching the structure of events and logs rather than the content of individual user messages. If your analytics events are supposed to include only certain fields, runtime monitoring can detect when a new field appears or when a field begins carrying unexpected values. For example, an event field that was expected to carry a category might begin carrying full free text, which could include sensitive terms. A field that was expected to be null might suddenly include an email or phone number because a developer reused a variable. Beginners sometimes think schema monitoring is too technical, but conceptually it is straightforward. You are comparing what is allowed to what is being omitted. When discrepancies appear, you investigate and correct them before they become widespread. This approach respects privacy because it focuses on structural anomalies rather than on reading people's content. It also creates a measurable control because you can define what fields are permitted and alert on violations. When schema monitoring is paired with clear event definitions, teams can innovate while keeping privacy boundaries firm. Runtime monitoring also includes watching outbound data flows, because privacy regressions often occur when new third-party destinations appear. A mobile app update might introduce a new SDK endpoint, or a web page might load a new script that sends data to an advertising network. Even internal changes can create new destinations, such as forwarding logs to a new observability provider. Monitoring outbound flows means maintaining an approved set of destinations and detecting when traffic appears to unknown or unapproved domains, especially when identifiers or content-like payloads are involved. Beginners might assume third-party additions are always obvious, but many are hidden in dependency updates and embedded components. When monitoring detects a new endpoint, teams can quickly determine whether it is legitimate, what data is sent, and whether user choices and vendor restrictions are being respected. This is a powerful drift control because it catches changes that may never appear in a product requirement document. It also supports vendor governance by revealing whether a vendor added a subservice or changed routing. When outbound flow monitoring is part of daily operations, privacy regressions have less room to hide. Retention drift is another runtime issue that must be monitored because retention is often managed through configuration and operational defaults, not through application code. Logs might be retained longer after an operational change, analytics systems might keep raw events longer than intended, or backups might preserve snapshots beyond the expected period. Monitoring retention means checking whether data stores enforce the retention periods recorded in policy and inventory, and whether deletion processes are running as expected. Beginners often assume retention is a static setting, but in practice retention can change when teams migrate systems, adjust storage tiers, or enable new troubleshooting modes. Another common issue is that retention may be enforced in one store but not in downstream replicas, which creates an illusion of compliance while data persists elsewhere. Runtime monitoring can detect this by checking whether data older than the retention limit still exists in stores where it should not. This kind of monitoring does not require reading personal data. It requires checking timestamps and counts, which is privacy-respecting and highly actionable. When retention drift is detected early, teams can correct configuration before long-lived exposure accumulates. Retention monitoring turns a policy promise into an enforceable operational behavior. Monitoring user control effectiveness is also essential because controls are meaningful only if they change real data processing. A privacy setting might claim to disable targeted ads, but if the system continues sending identifiers to advertising partners, the control is deceptive. A location setting might claim to use location only while the feature is active, but if background location events continue, the control is broken. Runtime monitoring can test control effectiveness by examining whether data flows change when settings are toggled, using test accounts or controlled environments rather than monitoring real users. Beginners sometimes think this requires invasive observation, but it can be done with structured tests that verify routing behavior and payload changes. It is also useful to monitor for situations where a control is honored in one platform but not another, such as a setting working on the web but failing on mobile due to different code paths. When control effectiveness is monitored, teams can detect regressions introduced by new releases quickly. This is crucial for trust because users judge privacy by whether the product respects their choices, not by whether the product offered a checkbox. Monitoring makes those choices enforceable over time. A mature approach also recognizes that privacy regressions can come from model changes in data science pipelines, not only from application code. A new recommendation model might introduce new input features that require additional data collection or that increase linkability across contexts. A new fraud model might store longer histories or create new risk scores that affect user treatment. Even if the UI looks unchanged, the underlying processing can shift, changing privacy impact. Privacy-aware review and monitoring, therefore, include tracking changes to data pipelines, feature engineering, and model inputs, ensuring that new data use is justified and that derived data is governed with retention and access controls. Beginners sometimes treat machine learning as separate from privacy engineering, but model pipelines are data pipelines, and they can introduce the same risks of overcollection and retention creep. Monitoring here can include checking what datasets are being used, whether sensitive features are present, and whether outputs are being stored and shared. It can also include verifying that training data retention is bounded and that vendor platforms are not reusing data for unrelated purposes. When model changes are governed, privacy regressions and automated decision systems are less likely. To make code review and runtime monitoring work together, teams need a clear definition of privacy-related guardrails, meaning the boundaries that should not be crossed without explicit review. Guardrails can include forbidden data fields and telemetry, restricted destinations for outbound traffic, approved retention limits, and required behavior under user settings. The most effective guardrails are those that can be checked automatically, such as schema validation for events, automated scanning for logging of sensitive fields, and alerts for new third-party endpoints. Beginners may assume automation replaces judgment, but automation supports judgment by catching common patterns and freeing humans to focus on nuanced decisions. Guardrails also need ownership because alerts without responsible responders become noise, and teams learn to ignore them. A healthy approach defines who investigates a regression alert, how quickly, and what actions are available, such as rolling back a release, disabling a feature flag, or hotfixing event payloads. It also defines how findings are documented and fed back into standards, so the same regression does not repeat. When guardrails, automation, and ownership align, privacy monitoring becomes a reliable operational capability rather than a reactive scramble. Finally, preventing privacy regressions requires a culture that treats privacy issues as defects to be fixed, not as optional improvements to consider later. When teams see a regression as a bug, they allocate time to remediate it, they verify the fix, and they add tests to prevent recurrence. When teams see regressions as normal or acceptable, privacy drift becomes inevitable, and the organization gradually becomes more invasive without deliberate choice. Beginners sometimes worry that this mindset slows innovation, but the opposite is often true because clear guardrails reduce uncertainty and reduce late-stage surprises. Teams can build faster when they know which fields are allowed, which destinations are approved, and what controls must exist. Culture also matters because privacy regressions often appear in stressful moments, such as incident investigation or performance troubleshooting, when teams are tempted to log everything. A privacy-aware culture supports temporary measures with time limits and rollback plans so emergencies do not become permanent expansion. When culture supports guardrails, code review and monitoring become normal quality practices. Reviewing code and monitoring runtime for privacy regressions is the practical way to keep privacy design promises true as products evolve. You begin by recognizing that regressions are usually small, accidental expansions in collection, sharing, retention, or control effectiveness that change the system's privacy profile. You build privacy-aware code review habits that scrutinize logging, analytics, identity linkage, and third-party integrations because those are common regression sources. You complement code review with runtime monitoring that watches what the system actually emits, where it sends data, how retention behaves, and whether user choices change data routing in practice. You include model and data pipeline changes because privacy drift can occur through derived data and automated decisions even when the interface stays the same. You define guardrails that are measurable and automate checks where possible, then assign ownership so alerts lead to action rather than noise. You treat privacy regressions as defects to be fixed and verified, building a culture where privacy is part of quality and trust is protected against slow creep. When these practices are in place, the organization can ship quickly while still maintaining stable, predictable privacy behavior over time, which is exactly what trustworthy products require.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.